Okay, so we've looked at pure strategy Nash Equilibria, and we've looked at them in a variety of different sorts of games. And I think now it's time to move on to mixed strategy Equilibria. And in order to figure out why we are interested in understanding randomization in games, let's go back to a variation on an example that we saw before of a predator-prey game. So in particular, this is a different example from the Shi and Bao paper that we looked at earlier, the 2008 paper, where they're looking at predator-prey games. And in particular, this one is based on insect instead of large mammals. And so here we have a different set of payoffs from being active and passive. And so the 2x2 matrix is listed here for the payoffs to active and passive for both predator and prey. So recall, in terms of a pure strategy equilibrium, we're looking for, if we wanted pure strategies, we're looking for a set of actions such that everybody's best responding to everyone else. And so we're keeping track of actions still. Now, if we begin to try and solve this game, what do we see? Well, first of all, let's suppose that we were looking at the actions of the predator. What should the predator do? So we look at what the prey is doing. If the prey is active, then the predator wants to be passive. Okay, so let's see if we could find an equilibrium where the predator is passive. Well, if we try and see whether or not this entry is an equilibrium, we're going to have some difficulties. Why is that? Because in this case, if the predator was actually passive, then the prey gets a -6 here, a 0 here. So we're in a situation where they would like to go in this direction. So if the predator was actually passive, then the prey would prefer to be passive. They can save calories by being passive once they're dealing with passive predators. But once we do that, once we look at that, then what happens now, we end up seeing that if the prey is going to be passive, well, then an active predator catches a lot more prey, and so then the predator wants to be active. So we think, okay, well, none of the other ones have been stable so far, maybe this one works, but here when we see if indeed the predator is going to be active, then the prey also wants to be active. And so the -7 is better than the -8. And so what we've got is a cycle here where none of the combinations of actions form pure strategy Nash equilibrium. So no matter which pair of actions we put together, somebody wants to deviate from that. Somebody has a different action which is a better response, a best response, and so we end up having a cycle, and we don't find any stable pure strategy Nash equilibria in this particular game. So what do we do? Well, the problem is that the prey wants to match what the predator is doing, and the predator wants to mismatch, and so in this kind of game we're not seeing any steady points. So this brings us to mixed strategy equilibria. So in order to define mixed strategies, what we're going to do is allow the players to randomize. Instead of just picking one action for sure, they might choose different actions with different probabilities. So in order to do that, let's define mixed strategies very carefully now. So in particular, we're still sticking with our AI as the pure actions that each player has available, and for now let's stick with the situation where these are finite sets, so let's take these to be finite. And then we can talk about the set of probability distributions over these. So SI now is a set of probability distributions over the actions. So each player, instead of just picking one action, is picking a way in which they're going to randomize over their actions. So maybe they pick that they want to be active 2/3 of the time and passive 1/3 of the time, or maybe half and half, or 7/8, 1/8. So they're picking a different probability over their different actions. So a mixed strategy for a player then is just a choice of a particular distribution, and the notation we'll use is that SI of AI is the probability with which player I plays a particular action. So that'll keep track of what probability they're playing each action with. Then we can also think of pure strategies in this world can be thought of as degenerate mixed strategies where you're putting weight 1, probability 1 on a particular action. So sometimes we'll go back and forth, but we can think of pure strategies as special cases of mixed strategies where you're just putting all your probability on one particular action. Okay, so now with our notation, then we can begin to, in order to talk about equilibrium, we're going to have to talk about best replies. We need to talk about the structure of the payoffs again. So in particular, now with mixed strategies, what we're going to assume is that players maximize their expected payoff. So they are maximizing just the overall expectation of their payoff when they try and choose a strategy. So the expected payoff of a given player, when she chooses a pure action AI and her opponents play mixed strategy S minus I, we can just think of that. So what's the payoff to I from playing AI? Well, we can just look at the overall probability distribution given what the other players are doing over their actions. So S minus I over A minus I now is just the overall probability of A minus I being played given a profile of mixed strategies of the other players. So we sum across the possible A minus I's and we get a total number here, which is their expected payoff conditional on what the other players are doing and a given strategy for themselves. So then if we want to just figure out what the payoff is for a particular randomization for a given player, then we're just going to take this thing we've just talked about, the expected payoff for a given action, and then we just sum across how much weight they're putting on each action, and we end up with a total overall expected payoff. So we can keep track now of a U of the profile of mixed strategies of all the players as opposed to just the pure strategies. So this is just a direct extension now where they're maximizing expected payoffs given the probability distributions over actions, and is a straightforward generalization of what we were looking at before. Okay, so our definition of mixed strategy Nash equilibrium is analogous to what we had before in terms of pure strategy Nash equilibrium, except now we're dealing with the randomized strategies and the associated payoffs. So we say that a mixed profile of mixed strategies S is a mixed strategy Nash equilibrium if a given player strategy SI is the best response to the actions, the mixed strategies of all other players. So in particular, the payoff that player I gets from playing SI is at least as high as they would get from playing any SI prime alternative strategy given the mixed strategies of all the other players. So let's take a look at how this works out when we go to the predator-prey games. So we saw that there was no pure strategy equilibrium, so let's begin to talk about mixed strategy equilibrium in this game. So let's let S2 of active, so the column player we'll call player 2, the prey. So S2 of active is the probability that the prey is active. Just to simplify notation so we don't have to carry that around everywhere, let's just let the letter P be the probability that the prey is active. Okay, similarly, let's let Q be the probability that the predator is active. And now, in solving for an equilibrium, let's look for an equilibrium where we think all four actions are going to be used. So we'll look for a situation where the predator is actually going to be using randomization mixing over both active and passive, so have non-trivial probabilities on both, and where the prey is going to have a non-trivial probability on both. So P is the probability that the prey is active. That means that there's a 1 minus P probability that the prey is passive. And so based on that, then we can go ahead and, if we are assuming that the predator is going to use both active and passive in their randomization, then it has to be that those are both best responses to the P and 1 minus P of the prey. That means that the payoff to playing active has to be equal to the payoff of being passive. So for the predator to be indifferent between these two strategies, we can look at what's the predator's payoff to being active. Well, that payoff is just 2 times the P and 6 times the 1 minus p. So we get this over here as the payoff to being active if the prey is being passive with probability 1 minus p and active with probability p. That has to be equal to the payoff that they get down here from choosing passive. And that's going to be 3 times the p and a minus 1 times the 1 minus p. So we end up with this equation for the predator to be indifferent between the payoff, the expected payoff of playing active or passive. For both of these to be best responses, for them will be willing to randomize between these two, they're going to have to satisfy this equality. So let's solve that. Well, if we solve that equation, simple equation, 7 times 1 minus p is equal to p, or p is equal to 7/8. So that tells us in order for the predator to be indifferent between playing active and passive, so to be willing to put probability on both, then the prey is going to have to play 7/8 on active and 1/8 on passive. So we have solved for what the prey's strategy has to look like in a mixed strategy equilibrium in order to keep the predator indifferent. Now let's reverse things and do the same calculation on the other side. So we go through that. Remember that Q is the probability that the predator is active. You can do the same calculation. So now we've got a Q here, a 1 minus Q here. We want the prey to be indifferent between choosing active and passive. So we can figure out what's their payoff going to be based on these rates if they choose active, if they choose passive. Set those two things equal to each other. That gives you an equality. Solve that, you get 6/7 for Q. So the predator has to be being active 6/7 of the time and passive 1/7 of the time in order for the prey to be indifferent. So what have we got? We've got a mixed strategy equilibrium. These are the relative probabilities that the different actions are played. So there is a Nash equilibrium to this game, even though there's no pure strategy Nash equilibrium. But there is one in which 7/8 of the insects, or 7/8 of the time, insects are active, 1/8 of the time they're passive, and 6/7 of the time the predators are active, and 1/7 of the time they're passive. Now just in order to talk a little bit about the interpretation of this, obviously this brings up a question of what really is randomization here. And I think one way to interpret this is not necessarily that any particular prey is active and passive with some probability, but that when you look at predators and they meet different kinds of prey, 7/8 of the ones that they meet are active and 1/8 of the ones that they meet are passive. And vice versa in terms of prey. What the important thing is in terms of the expected what strategy that they're going to face on the other side has to have these particular probabilities in order to balance and be in equilibrium. But now, how we interpret this can vary depending on the actual application. So we'll talk more about interpretations of mixed strategies as we go along.